Merhabalar. Hi. Today I want to present you my project about the feature of efficient attitude and trust control, obviously presented by me, Dora Saylıkoğlu. So let's jump right in. So let's talk about what is an ion thruster. So first, normal typical rockets use chemical propulsion or conventional propulsion techniques by combining normal oxidizer and fuel together to make a reaction hot and energetic enough to go just pump it out of the rocket. But ion thrusters are kind of different. They use electricity. They use electricity to produce these high energies in the field. Also, if you actually read the name, the ions, there are of course ions there. Uh, and these ions, and if we want to talk about what an ion is a particularly special kind of atom. In normal atoms, the proton number is the exact same as the electron number. However, when sometimes these atoms can get weirder and the electron number can be bigger or smaller than the proton number. If the electron number is bigger than the proton number, we call them anions. And if it's smaller than the proton number, we call them cations. And if the ions are, because there is a um, imbalance between the proton and the electron count, they are also electrically charged. If they are an excess electrons, they are negatively charged, and they don't have this they have less than the proton number. They are positively charged, and charged particles can be moved around in electric or magnetic fields. Also, ion thrusters are like kind of different, actually lots of different than and the conventional engine. It says that it gives little thrust but with massive efficiency. In the next slides, we're going to talk about what that means. So let's talk about the mechanism of an ion thruster. So if you so sorry. So here is the electron gun, and uh, near it, we just push the normal propellant atoms. So these propellants are usually noble gases in an ion thruster. So when we just I guess put them together, these neutral atoms and electrons, these electrons actually knock to the neutral atoms, and these electrons knock off the neutral atom's electron. Because there's the electron number is smaller than the proton number, these propellant atoms become positively charged. And if you see it, the green atoms become positively charged blue atoms. So then, with the help of either a magnetic or an electric fields, as you can see, we need to create a voltage with a positive and negative grid to propel them. Then we uh, thrust them, I guess, um, like out of the nozzle, and these positively charged atoms. And we want to keep everything nice and neutral, so we also like propel the electrons that was in the chamber with the positive atoms, so the exhaust is nice, sturdy, and neutral, so it won't be affected by the engine or the rocket itself. Yes, as I explained it, the process is mainly about ionizing noble gas or the fuel and sending them through an electric and magnetic field. This ends up in a super efficient and super long duration thrust. Let's compare these engines. So, um, Your ion thrusters generally use noble gases like xenon or argon, and chemical propulsion uses RP rocket propellant 1, methane, liquid hydrogen, with an oxidizer like liquid oxygen. If you look at the ion thruster, the efficiency is between 70 and 90%, which is really high, but in chemicals, it's 30 to 35%. And if you look at the thrust, this is where ion thrusters lack at. It gives the maximum of a 5 Newton, but generally around 30 to 40 millinewtons of thrust. Milli is like 1,000 of a Newton, and a chemical propulsion gives about 1 to 12 mega newtons, which is 10 to the 16 newtons. However, exhaust speed wise, ion thrusters obviously because it can give out to 90 kilometers per second, and the chemical just gives about 45. And specific impulse. Specific impulse is a way to like um, measure efficiency, and the higher the sequence is, the better the more efficient it is. So if you look at there are almost 5,000, and in chemical is about 200. In ion thrusters, the way we like give about the electrons is via electricity, is whether from solar or nuclear, and in chemical propulsion, it's about from chemical reactions. And the thrust durations, ion thrusters, because it's so efficient, it can continue to run for days, weeks, and months. However, chemical propulsion usually uh, use around a couple of minutes at maximum. So yes, I guess almost the only place where the ion thrust lack is low thrust, because we're pushing electrons that isn't with high voltage, and these electrons and uh, atoms are very lightweight, because we usually use gases like argon and xenon. It has low thrust. Maybe we should, yes, give it some more lightning McQueen or electricity. Okay, there are some examples of ion thruster uses. There has already been a couple of ion thrusters already using space, which is, for example, BP Colombo and Dawn missions. BP was sent to Mercury, and Dawn was sent to protoplanets like Sirius and Vesta. They are very long distance long distance spacecrafts. So I actually kind of tried to do my own ion thruster from paper and such. So you can see that I use paper, tape, hot glue gun, balloon, and straws. So for the first step, I turned my paper into a cylinder using tape, and then I cut in half um, my straws, and then stick them together with hot glue gun, and then glued them to my balloon. Then I ended up with this, which is kind of looking like dumb, but it's actually a really good example of how it works, how an ion thruster works. So if you put them together, as you can see, as I pumped air into the balloon, it kind of resembles the ionizing xenon in an ion thruster. And then there is the nozzle, and the like straw resembles an electric or magnetic field. Then it propels the air, or I guess in this case fuel, through the nozzle, the paper nozzle, and then it acts like a thruster. So thank you for listening to me. I hope you like my project. I guess it's the DIY is really easy, and if you see it, you can really learn so much about what ion thrusters do and such. Thank you for listening to me, and see you next time.